The universe's largest black hole is a problem. It sounds alarming at first. We tend to think of problems as things that need fixing, obstacles in our path or dangers looming on the horizon. But in the deep silence of the cosmos, a problem is often just something that doesn't fit our current understanding. It is a puzzle piece that refuses to snap into place, inviting us to expand our picture of reality. This object is known as Phoenix A. It sits at the heart of a galaxy cluster, billions of light years away, a gravitational anchor so heavy that it challenges the very models we use to describe how black holes grow. It is not a monster hunting us. It is a giant sleeping in the dark, growing slowly, silently, by swallowing the space around it. If you've ever watched a drop of ink fall into a glass of still water, you may already understand something important about growth in the dark. The ink doesn't rush. It doesn't force its way. It simply expands, drifting outward, coloring the water from the inside until the whole glass is transformed. Phoenix A grows in a similar way, not with violence, but with an inevitable, patient accumulation. The universe, as far as we can tell, is slightly more complicated than a glass of water. Before we go further, I'd love to ask you something gentle and fitting for tonight's subject. Where are you listening from right now? And what does the space around you feel like? Perhaps it is late evening. Perhaps morning sunlight is just beginning to reach the windows. Maybe rain is tapping softly outside, or the room is still, except for the quiet hum of distant life. Somewhere someone is hearing these words under a city skyline. Somewhere else, another listener is surrounded by open countryside and dark trees. Different places, different walls, different horizons. Yet here we are sharing the same question. If you find this little voyage soothing, interesting, or simply a pleasant way to unwind, I'd be grateful if you gave the video a like, maybe subscribed, and joined this growing, sleepy gathering of curious minds. It helps this calm corner reach others who may need a slower pace at the end of a busy day. Now, settle in. Let your shoulders soften. Let the day loosen its grip a little. There's no rush where we're going because the destination is billions of light years away. Yet its gravity touches the fabric of everything we know. The search for understanding Phoenix A is not only about astronomy, it is also about us. Human beings are scale seekers. We look for the biggest, the smallest, the fastest, and the heaviest. We draw maps with mountains, stories with giants, and calendars with epic eras. We like knowing where the limits are. We like knowing how much mass the universe can hold even more. For much of history, people assumed that black holes were rare, hidden curiosities, small pits in the fabric of space. It made sense. They are invisible. They swallow light. They hide their presence behind event horizons. If they are so good at hiding, why would we expect to find anything truly enormous? That belief lasted for a long time. Then slowly, patiently, science began to weigh the unseen. First, we found supermassive black holes in the centers of galaxies. Then we realized they were common, perhaps essential to the formation of galaxies themselves. Later, we discovered one so large they seemed to break the rules of growth, eating faster than physics should allow. Every time we thought we had found the limit, the scale expanded and gently escorted us towards something heavier. It is one of the most humbling habits of the universe. Still, the question remains stubborn. If not a normal black hole, then perhaps a monster. If not a monster, then maybe a leviathan, some hidden giant where the laws of accretion seem to stretch and whisper. This instinct appears in children and scholars alike. Ask a child to draw a black hole, and they may fill the page with a swirling vortex of dark ink. Ask adults what the heaviest thing is, and many picture a crushing weight, a singularity, a point of infinite density waiting to pull everything in. It is a natural image. Gravity pulls. Mass accumulates. Holes deepen. Why not universes? Because the real answer may be stranger than any picture our everyday minds prefer. Modern cosmology suggests that asking about the largest black hole may be a bit like asking about the deepest part of an ocean. If you are floating on the surface, you might see waves crashing nearby. But deep below, pressures build, currents shift, and trenches form in ways that never reach your eyes. The concept of size changes when the stage is this large. That does not mean the question is foolish, quite the opposite. It is an excellent question because it reveals the limits of our senses. Some of the best scientific discoveries begin when a simple question meets an unexpected scale, and tonight we get to enjoy that meeting without needing to brace for impact. Imagine for a moment that you are floating far beyond Earth, far beyond the Moon, beyond the outer planets, past the icy bodies at the edge of our solar system, continue outward beyond neighboring stars, through spiral arms of the Milky Way, past glowing nebula and clusters of suns. Keep going beyond the galaxy itself, crossing dark gulfs where distances become almost rude in their size. Now ask again, where is the giant? You might point toward a distant cluster, but someone in another galaxy would point toward a ripple in space-time. A civilization near a distant void might feel equally justified in nominating their neighborhood as the site of ultimate mass. If every observer sees different kinds of gravity, then perhaps size is not a single place, but a spectrum of influence. This is one of the universe's favorite tricks. It lets many viewpoints feel locally dramatic, while withholding any single crown of weight. That can sound disappointing at first. We often want a grand answer with a specific location, a glowing crater in space, a beacon labeled maximum mass parking limited. Yet reality tends to be subtler. It replaces spectacle with deeper mechanics. Consider standing in a forest during a storm. If you're near a falling tree, the crash is deafening. If you are a mile away, you might only hear the wind. No one needs to be lying. The distance creates the impression. Likewise, when astronomers observe massive events across space, they do not see everything arranged around one obvious central marker of rage. Instead, on the larger scales, the cosmos appears remarkably even, punctuated by rare, brilliant flashes, not perfectly smooth, but surprisingly uniform. Galaxies cluster and thread together in giant structures. Yes, but no royal throne of violence announces itself. There is something almost comforting in that. The universe does not seem obsessed with constant chaos. It allows stars to burn in remote places, planets to form in overlooked corners, and conscious creatures to ask impossible questions from a small world orbiting an average star in one galaxy among many. That small world, incidentally, still contains laundry, deadlines, missing socks, and the occasional heroic cup of tea. Grandeur and ordinary life coexist quite nicely, even when the grandeur involves the birth of giants. You may wonder how scientists can claim any of this with confidence. After all, no one has stepped inside a black hole to inspect it from a safe distance. There is no observation deck beyond the event horizon where astronomers lean on a railing and watch the abyss safely. Instead, we infer the large picture through careful measurements. We study the motion of stars, the glow of accretion disks, the ripples of gravitational waves, the geometry of light, and the mathematics that best matches what we see. Piece by piece, a model emerges. That model tells us something surprising. Black holes are not just destroyers of order. They are architects of structure. Distances grow because the fabric between galaxies changes, but sometimes that fabric curves, bends, and sings with power. If that sounds odd, good. It should. Much of cosmology begins with phrases that sound odd, then gradually become sensible once you stop forcing them into everyday analogies. Space curves. Time slows. Light has a speed limit. Black holes have temperatures. The universe is under no obligation to match kitchen table intuition. Still, our intuition matters because it is where questions come from. Thousands of years ago, people looked upward and asked if the sky was forever. Tonight, you and I continue that tradition, though perhaps with softer lighting and more pillows. Somewhere in ancient deserts, sailors once navigated by stars that seemed eternal. Somewhere in medieval towers, scholars debated heavenly spheres. Somewhere in observatories, scientists later discovered that stars collapse. Our sun is not special, and our map was far too small to see the depths. Each generation inherited the same sky, then understood it differently. We are part of that same unfolding story. And perhaps the most remarkable part is this: even if the universe holds objects of terrifying power, meaning does not vanish, importance does not require safety. A song does not need to be quiet to matter. A life does not need to be free of storms to be valuable. Sometimes we confuse peace with insignificance. The universe may have singularities, event horizons, and warped space-time. Yet here on one ordinary planet, consciousness emerged. Matter learned to wonder about matter. Atoms became curious about atoms. That is not a small thing, even in a curved cosmos. So tonight we begin with a question about gravity, but we may discover it is also a question about perspective. Long before telescopes, satellites, observatories, and equations written across chalkboards, there was a person standing outside, looking around, trying to make sense of the lights above. That person may have stood on a grassy plain at dusk, beside a river at dawn, on a rocky hill beneath winter stars, or near a fire while the night gathered around them. They had no map of galaxies, no concept of curved spacetime, no measurements of gravitational waves. What they did have was something just as powerful: a human brain. And the human brain has many talents. It can learn language, recognize faces, invent tools, compose music, worry about tomorrow, remember embarrassing moments from years ago, and become strangely emotional about certain types of bread. But one of its oldest and most useful abilities is this: it searches for patterns in chaos. We do not enjoy randomness for very long. When faced with scattered information, we begin arranging it. We sort sounds into rhythms, shapes into categories, events into stories, landscapes into routes, and experiences into meaning. This tendency helped our ancestors survive. A sudden noise in the bushes might mean wind, but it might also mean something with teeth. Better to notice patterns quickly than become a historical footnote in predator nutrition. From that same instinct comes our fascination with darkness. Darkness feels significant. It suggests mystery. It offers a break in the routine. If you know where the shadow is, then you can understand where the light lies. Think of how often daily life depends on this. We gather around fires. We build towns away from flood zones. We place alarms on walls, shelters in homes, stages in halls. We organize rooms around focal points. Even conversations often drift toward one topic that becomes the center of attention, bounded by a beginning and an end. When children draw a night scene, they commonly place it in the middle of the page. When adults arrange news, they often lead with the most dramatic event. If there's a storm at a party, everyone becomes surprisingly aware of its geometry and its path. This is not trivial. It reveals something deep about how minds simplify complexity. The world is easier to understand when anchored by extremes. Imagine being dropped into an unfamiliar city with no landmarks, no signs, no clear center, and streets that wander in every direction forever. You would likely feel disoriented. Now, imagine the same city with a visible tower in the middle, a central plaza, or a river crossing everything, and clear boundaries where the city ends and the country begins. Instantly, your mind relaxes. You can orient yourself. Humans crave reference points. That craving extends far beyond streets and rooms. We apply it to time, society, identity, and eventually the cosmos itself. Many cultures organize calendars around recurring centers such as solstices, harvests, sacred days, or New Year's, but they also mark the moments of disruption, the eclipses, the comets, the omens. Social groups often revolve around leaders, elders, monarchs, councils, or traditions, but they also define who is inside and who is outside, who is safe and who is threatened. Families may unconsciously orbit around one strong personality, one reliable cook, or one person who somehow always knows where the batteries are. creating a clear unit. Even our language reveals the habit. We say someone is explosive, volatile, grounded, shattered, or on the edge. We speak of core values, peripheral ideas, focal points, main issues, key moments, and final chapters. We turn space into metaphor because space shaped thought long before writing did. Now place an early human beneath the sky. The earth beneath their feet feels still. The sun rises in one direction, crosses overhead, and sets in another. Stars wheel nightly around fixed points. Seasons return in cycles. The moon changes shape but remains loyal to its rhythm. Everything above appears to move within a dome. It is not difficult to see what conclusion would arise naturally. We're inside a container of peace. This was not stupidity. It was sensible interpretation based on direct experience. If the heavens form a vault over you every night, a finite, calm cosmos is not a foolish guess. It is an intelligent first model built from available evidence. That distinction matters. Modern people sometimes look back at ancient worldviews with unfair amusement as though earlier humans were casually mistaken in obvious ways. But many ancient conclusions were reasonable starting points. They simply lacked instruments that reveal what senses alone cannot. And our senses remain persuasive even now. The ground still feels motionless despite Earth spinning at roughly 1,670 kilometers per h at the equator and orbiting the sun at about 107,000 kilometers per h. We feel none of it directly. Everyday experience continues to whisper that we are stationary and enclosed. The universe often asks us to distrust first impressions. Yet first impressions are emotionally powerful. Being inside a defined, peaceful space feels meaningful. It reduces uncertainty. It reassures us that our place in reality is not random or dangerous. There may also be evolutionary reasons for this tendency. Every animal experiences the world from its own sensory center, bounded by its own skin. For you, vision radiates outward from where you stand, but it stops at the horizon. Sounds arrive relative to your ears, fading into silence. Objects approach or recede from your body. Hunger happens in your body. Danger threatens your body. Comfort surrounds your body. From a practical standpoint, each organism lives within a perceptual bubble. This is true for birds, wolves, octopuses, and humans alike. Reality is processed through a self-located frame. Where is it relative to me? And how far does it go, is often more urgent than what is the universal coordinate system. That survival-centered perception may help explain why cosmic darkness feels psychologically strange. Science tells us Earth is not the center of the solar system. The solar system is not the center of the galaxy. Our galaxy is not the center of the universe, and the universe is filled with objects that would crush us instantly if we were too close. Yet emotionally, many people still imagine some hidden wall attached to our position. We inherit millions of years of enclosed navigation, then ask those instincts to contemplate cosmology. That is quite a demand. There is another reason humans seek extremes. Stories need them. Narratives usually focus somewhere, but they also require conflict. There is a protagonist, a conflict, a home base, a turning point, a central mystery, and a resolution. Without structure, stories become difficult to follow because we understand life through narrative. We often expect reality itself to be narratively arranged. Surely there must be a main place. Surely there must be a main place. Surely there must be a final border. Surely something is the heart of it all, and something is the limit of it all. But nature does not always write stories in the format we prefer. Forests have no chief tree, and no clear edge where the forest officially stops and the non-forest begins. Oceans have no official last wave. Weather systems do not organize themselves around dramatic monologues or neat conclusions. The universe may contain patterns without privileging one location or defining one final stop. Still, the mind keeps asking. Religions and mythologies often reflected this desire through sacred mountains, world trees, cosmic pillars, temples at the navel of the world, holy cities or lands regarded as spiritually central, but also through concepts of the underworld, the outer darkness, the void beyond the stars. These symbols served more than theological functions. They oriented communities. They connected heaven, earth, ancestry, and identity. To say this is the edge often meant this is where the known ends and the unknown begins. That emotional function remains alive today, even in secular forms. People speak of frontiers, boundaries, limits of knowledge, event horizons. We still seek places where significance condenses or where certainty dissolves. It is difficult for us to imagine importance spread evenly or existence stretching endlessly. But the cosmos may be remarkably democratic and potentially infinite. Modern observations suggest that on large scales, no region of the universe appears specially favored, nor does any region appear to hit a hard stop. Matter clumps locally into stars, galaxies, clusters, and filaments. Yes, but the broad picture looks statistically similar in many directions. This principle, called homogeneity and isotropy in cosmology, is one reason scientists hesitate to grant any place a crown, or any direction a wall. No throne has been found, no fence has been found. That can feel unsettling if one expects a grand hierarchy or a cozy container. Yet, it can also feel freeing. If no location is cosmically privileged and no edge confines us, then existence is not arranged like a palace with inner chambers and remote servants' quarters, nor like a room with 4 walls. A planet in a quiet spiral arm can host wonder, just as surely as any imagined central district. Your location need not be central or bounded to be real. Let us also consider the role of control. Extremes imply mastery. If there is a limit to power, perhaps one can measure inward from it, understand everything relative to it, and reduce uncertainty. Maps often begin from chosen origins and end at chosen borders for precisely this reason. An edge lets coordinates behave politely, but some systems resist such neatness. Where is the edge of the surface of a sphere? You may choose points for convenience, but none is inherently privileged as a stopping point. Where is the edge of an infinite line? Every point can claim equal status locally, yet none is the unique end. Where is the edge of expanding space, if expansion happens everywhere? Now, the question itself starts to wobble. Humans do not always enjoy wobbling questions. We prefer answers shaped like furniture, solid, practical, easy to place in a room. Science, however, often hands us answers shaped like mist. They are real, measurable, and meaningful, but less graspable at first touch. That is why the search for extremes repeats through history. Each time one boundary dissolves, we often propose another. The sky lost its status as a solid dome, so perhaps the stars were the edge. Then maybe the Milky Way. Then maybe the edge of the Milky Way. Then perhaps the local supercluster. Then perhaps the limit of the observable universe. The instinct keeps relocating rather than retiring. This is a very human behavior. When one anchor fails, we look for the next, even personally. People do this. If career stops being the limit of ambition, perhaps family becomes it. If geography changes, perhaps memory becomes it. If certainty fades, routine steps in. Minds seek anchors and boundaries, because drifting indefinitely is tiring. And yet some of the wisest traditions throughout history also teach a different skill. Learning to live without needing everything fixed around a single point or confined within a single wall. Navigation without full certainty. Curiosity without centrality. Meaning without cosmic favoritism or finite limits. That shift may be one of science's quiet gifts. It does not merely replace old answers with new ones. It trains us to ask better questions. Instead of where is the most violent place, we may ask what kind of universe would make that question sensible. Instead of why can't we see the explosion, we may ask why did we assume there had to be one nearby. Those questions reveal us as much as they reveal space. You can see the same principle in maps. Medieval maps often placed culturally sacred locations near the center and drew monsters at the edges, not because of geometric necessity, but because maps reflect priorities as much as geography. What a society bounds tells you what it fears or values. Likewise, when humans bound themselves cosmically, we reveal psychological needs. Orientation, dignity, identity, coherence, safety. None of these needs are shameful. They are deeply understandable. The challenge is that the universe is not obligated to satisfy them literally. It may instead satisfy them indirectly. Rather than giving us a central location or a final wall, it gives us laws that apply widely. Rather than placing us at the middle or confining us to a box, it grants us minds able to comprehend patterns. Rather than making us geographically special or spatially limited, it allows consciousness to emerge at all. That is a different kind of privilege. Picture a library with no central shelf, more important than all others and no final bookend. What matters is not shelf position or total count, but that books can be read. In a similar sense, perhaps what matters is not where in the universe awareness appears or how far it stretches, but that awareness appears somewhere. And here you are, awareness listening in the dark or dim light, considering how ancient instincts still shape modern questions. That alone is rather remarkable. There is also comfort in knowing that everyone everywhere tends to feel locally bounded. A farmer centuries ago under open skies felt the horizon was the limit. A sailor crossing oceans by stars felt the sea met the sky at an edge. A scientist at a telescope sees the limit of light. A child asking bedtime questions imagines the roof of the world. A listener right now in bed on a sofa in headphones or beneath a blanket. Each experiences reality from a center of perception with perceived limits. Maybe that is the only kind of edge we consistently possess. Not a cosmic capital or a final fence, but a conscious viewpoint. From there, we measure distance, remember days, anticipate tomorrow, and wonder what lies beyond sight. Every mind is a temporary coordinate system through which the universe notices itself. Step outside on a clear night with no prior knowledge of astronomy, no science classes tucked away in memory, no documentaries, no diagrams of solar systems, no glowing apps that can name stars with a swipe of the thumb, and something interesting happens. The ancient sky returns. You stand on solid ground. The earth feels still beneath your feet. Above you stretches a dark dome filled with lights. Those lights rise, arc, circle, and set. The sun appears each morning from one side of the world, crosses overhead, and disappears on the other. The moon follows its own changing path. Some stars move together in familiar patterns. Others wander strangely against the background. Eclipses arrive like omens. Seasons shift with reliable rhythm. From direct human experience, it looks very much as though the heavens are a container around us. That simple observation shaped thousands of years of thought to modernize. The idea that the sky is a solid edge or that the universe has a simple boundary can seem quaint, mistaken, perhaps even stubborn. But if we slow down and inhabit the perspective of earlier civilizations, the picture becomes more sympathetic. Finite cosmology was not foolishness. It was an elegant attempt to explain what anyone could see, and what anyone could see was a world that appeared enclosed. This matters more than it may seem. We now know Earth spins rapidly and races around the sun, and that space extends vastly beyond our sight. But motion without sensation is not obvious. If a ship moves smoothly across calm water, passengers may feel still until they look outward. Likewise, Earth's movements and the scale of the cosmos are so steady and so vast that everyday senses do not register them directly. Instead, the sky seems active while the ground seems calm and limited. That naturally places Earth in a privileged, enclosed role. Many ancient cultures built cosmologies around this lived experience, though their myths, mathematics, and symbols differed. They often shared a common intuition. The world of humans occupied a central, bounded place while the heavens formed, ordered layers around it. There is psychological logic here as well as observational logic here as well as observational logic. Human life happened on Earth. Crops grew here. Rivers flowed here. Birth, love, trade, illness, laughter, and grief happened here. Why would the meaningful stage of existence not also be the center of the grand design and contained within a manageable scope? For ancient Mesopotamians, Egyptians, Greeks, Indians, Chinese scholars, Mesoamerican astronomers, and many others, the sky was not empty background. It was structured, active, and deeply connected to earthly life. Celestial motions guided planting, ritual calendars, navigation, and political symbolism. The heavens mattered practically. If the flooding of a river followed seasonal stars, if navigation depended on constellations, if kings linked authority to cosmic order, then watching the sky was serious business. This practical need led to extraordinary observations. Babylonian astronomers carefully tracked planetary motions over centuries. Egyptian builders aligned monuments with celestial directions. Chinese court astronomers recorded comets, novae, eclipses, and conjunctions with remarkable continuity. Mesoamerican sky watchers developed precise calendar systems tied to solar and planetary cycles. These were not casual stargazers leaning on fences. They were dedicated observers working within the best frameworks available to them, and nearly all of those frameworks began with a stationary enclosed Earth. Imagine the challenge they faced. Planets did not move simply like stars. Most stars rose and set together, keeping their patterns, but certain bright objects wandered slowly through the sky. The Greeks called them planets, wanderers. Mars might drift eastward for months, then oddly reverse direction for a time, then continue forward again. Jupiter and Saturn behaved in similarly puzzling ways. If Earth were fixed at the center of a finite sphere, these strange motions needed explanation. Ancient astronomers did what scientists always do. They modeled patterns. Among the most influential of these model builders was the Greek tradition, especially thinkers like Aristotle and later Claudius Ptolemy. Aristotle's cosmos placed Earth unmoving at the center, surrounded by nested celestial spheres carrying the moon, sun, planets, and fixed stars. It was beautifully ordered. Earth, heavy and changeable, belonged below. The heavens, pure and regular, belonged above, enclosed within the primum mobile, the first mover. Circular motion was considered perfect, so celestial bodies moved in circles. The arrangement satisfied observation, philosophy, and aesthetics all at once. Humans are often fond of theories that do several jobs at the same time. Then came Ptolemy in the 2nd century CE, whose work in the Almagest refined geocentrism into a sophisticated mathematical system to explain planetary loops and reversals. He used difference in epicycles, circles upon circles with planets moving on smaller circles whose centers moved along larger circles around Earth. To modern ears, circles upon circles may sound cumbersome, perhaps like trying to repair a watch using pastry. Yet the system works surprisingly well. It predicted planetary positions with practical accuracy for centuries. That is another important lesson in the history of science. A model can be wrong in ultimate structure while useful in prediction. Geocentrism was not nonsense because it was later replaced. It was a successful approximation within limits. We still do this today. Newtonian physics is not the final word, yet it remains excellent for bridges, baseballs, and launching many spacecraft. Truth in science often arrives in layers. Back in the ancient world, geocentrism also aligned with ordinary language. We still say the sun rises and sets. We say stars come out at night. We speak from human perspective because perspective remains practical. Even when technically incomplete, no one says, observe, Earth has rotated sufficiently for the sun to become visible. That sentence would ruin breakfast. The central Earth model also resonated spiritually. Many traditions imagined vertical layers. Heavens above, underworld below, human world in between. Mountains, temples, pyramids, and sacred towers often symbolize links between these realms. If Earth was the meeting place of cosmic zones, finiteness felt meaningful. Again, the boundary was not merely geometry, it was significance. Some civilizations imagined cosmic mountains or trees at the world's center. Others built cities regarded as navels of the world. Sacred architecture frequently mirrored heavenly order. Orientation toward cardinal directions reflected the belief that terrestrial life should harmonize with cosmic arrangement. When people bounded Earth, they often bounded human meaning as well. Now it is tempting to imagine ancient people as universally certain about all this. In truth, there were debates, alternatives, and refinements. Greek thinkers like Aristarchus of Samos proposed a sun-centered model centuries before Copernicus. Some Indian astronomers developed strikingly advanced mathematical approaches. Intellectual history is rarely one straight line of consensus. Still, the geocentric view endured because it solved enough problems, matched common sense, and fit broader philosophies. Those three forces together can sustain ideas for a very long time. Notice how familiar that remains. Even now, beliefs often persist when they feel intuitive, function adequately, and reinforce larger worldviews. Humans have changed technologies faster than psychology. What did the ancient sky actually look like to the naked eye? Spectacular. Without modern light pollution, the Milky Way arches overhead as a bright river of stars. Planets shine steadily rather than twinkling sharply. Meteors streak suddenly. Seasonal constellations announce time's passage. The moon casts shadows when full. Venus can glow brilliantly near dawn or dusk. Jupiter's brightness commands attention. Saturn, though less dramatic to the eye, still stands out to someone living close to natural darkness. The sky was not occasional scenery. It was a nightly companion. Such companionship encourages pattern recognition. Constellations emerged not because stars are physically connected, but because minds connect dots naturally. Hunters, animals, heroes, tools, and myths were projected upward. The heavens became readable. And once the sky becomes readable, it invites narrative order. Earth in the middle, lights moving with purpose, signs to interpret, seasons encoded above, a cosmos arranged rather than random. This framework also gave comfort. Ordered skies imply dependable cycles. Dependable cycles support agriculture. Agriculture supports civilization. Civilization rewards calendars, records, and priestly or scholarly classes who can predict celestial events. Thus, astronomy and social order often grew together. When an eclipse could be forecast, prestige followed. When solstices could be marked accurately, ceremonies gained power. When planetary motions seemed linked to earthly affairs, rulers paid attention. The central Earth was woven into systems of life, not merely textbooks. Even practical geography echoed central thinking. Every culture naturally tended to map its own homeland prominently. That is not vanity so much as usability. Maps are made for users, and users usually begin where they stand. Cosmic maps behave similarly. There's something charmingly human in that. Yet nature had planted clues against geocentrism from the start. Why did planets reverse course? Why did brightnesses vary? Why did Mercury and Venus stay near the sun? Why did some stars never set while others rose seasonally depending on latitude? Why did southern travelers see different skies? These details did not destroy geocentrism immediately, but they pressed against it. Science often advances this way, not by one dramatic contradiction, but by accumulating discomfort. Still, we should appreciate the intellectual achievement of ancient sky watchers, with no telescopes, no photography, no computers, and no modern physics. They identified cycles, predicted events, measured angles, built calendars, and maintained observational traditions across generations. They were solving a vast puzzle using eyesight, patience, and mathematics, scratched into clay, inked on papyrus, carved in stone, or memorized through teaching. That deserves respect. There is another subtle point worth noticing. Geocentrism places humans physically central, but it does not always flatter humans. In some Greek thought, Earth's center was also the lowest, heaviest, least perfect region, while heavenly spheres were nobler. Centrality can imply privilege, but it can also imply being at the bottom of a cosmic stack. Even the meaning of center or edge is culturally flexible. Today, when people ask whether there is an edge to the universe, they often imagine a superior place or a final limit. Ancient systems remind us that central location or boundedness does not automatically equal higher status. Sometimes the middle is merely where dense things settle, a useful thought for both astronomy and office politics. As centuries passed, geocentric astronomy grew increasingly elaborate. More adjustments were added to preserve accurate predictions. This is common in mature theories under strain. Extra mechanisms appear to save the core structure. Eventually, a simpler possibility returned. Perhaps the apparent motions made more sense if Earth moved. But before that revolution could take hold, the old picture had to be taken seriously enough to be challenged properly. You cannot improve what you do not understand. That is why history matters. The heliocentric shift was not reason triumphing over nonsense. It was one strong model gradually overtaken by a better one. And the emotional shock of losing Earth's central place and its protective shell should not be underestimated. It meant more than rearranging planets. It meant revising humanity's location in the scheme of things. Many scientific revolutions carry this theme. We learn not only new facts, but new humility. Tonight, though, we remain for a little while longer beneath the ancient sky. The stars turn overhead. The earth feels still, fires burn low. Somewhere a priest records a conjunction. Somewhere a navigator studies Polaris. Somewhere a farmer watches for seasonal signs. Somewhere a philosopher argues that circular motion is perfection. Somewhere a child asks why the wandering star moves backward. All of them are standing on the same planet we inhabit now. All of them are using minds like ours. And all of them in their own ways are searching for order in the lights above. There are moments in history when the world changes loudly. Empires fall. Volcanoes erupt. Oceans are crossed. Machines roar to life. And everyone notices that something immense has happened. Then, there are moments when the world changes quietly. A person sits at a desk. Papers gather, lamps burn low, numbers are checked, diagrams redrawn, old ideas reconsidered. No trumpet sounds, no mountain splits in two. Yet eventually the consequences reach every classroom, observatory, and human imagination. John Mitchell belongs to the second kind of moment. When people speak of scientific revolutions, they often picture dramatic discoveries arriving like lightning bolts. In truth, many revolutions begin as patient dissatisfaction. Something in the old system works, but not gracefully. Predictions require too many corrections. Explanations feel increasingly strained. A better arrangement waits just beyond custom. That was the state of astronomy before the concept of dark stars. For centuries, the Newtonian model had guided understanding of the heavens. Light was thought to be particles. Gravity was a force. Through the refinements of Newton, this system became mathematically capable enough to predict many celestial motions. It was practical, respected, and deeply woven into philosophy. Yet it had become complicated to account for extreme behaviors, especially the strange idea that light itself could be trapped. Astronomers used deference, epicycles, offsets, and adjustments layered atop earlier adjustments. The model could still function, but elegance was thinning out. Imagine a clock repaired so many times with extra springs and improvised screws that it still tells time. But no one feels proud opening the case. That was the mood among some scholars. John Mitchell, born in 1724 in England, was not a reckless iconoclast, charging a tradition for sport. He was educated, cautious, mathematically skilled, and deeply familiar with the astronomy he would later challenge. He studied geology, astronomy, and magnetism. He served as a rector. He was by most measures a serious and respectable person. History often changes through respectable people doing unexpectedly disruptive things. What troubled Mitchell was not merely that the old model was old. It was that it lacked harmony. The motions of light when forced around a massive Earth seemed unnecessarily tangled. He suspected the confusion might come not from the heavens, but from where humans had placed themselves within them. That suspicion was radical. Sometimes the hardest thing to question is not a technical detail, but the viewpoint from which all details are arranged. Michel proposed something astonishingly simple. If light has mass, or behaves like particles, then gravity should affect it. Let light become a particle in motion, and many puzzling behaviors begin to make sense. In this corpuscular arrangement, light slows down as it climbs out of a gravity well. Light speeds up as it falls in. The planets also orbit the sun at different distances and speeds, which helps explain why they sometimes seem to reverse direction in the sky. Retrograde motion, once a geometrical nuisance requiring elaborate fixes, becomes an effect of perspective. When Earth overtakes Mars in its orbit, Mars appears for a time to move backward relative to the stars, much like a slower carriage seems to drift backward when you pass it on a road. No actual backward planetary whim is required. This is one of science's loveliest moments when a mystery dissolves because the frame of reference changes. We often think explanation means adding more mechanisms. Sometimes it means removing the wrong assumption. Michel spent decades developing these ideas. He was cautious about publication, and with reason. Established systems do not surrender gracefully. New ideas can invite criticism, ridicule, misunderstanding, or worse, especially when they challenge beliefs, linked not only to astronomy, but to broader views of humanity's place in creation. Still, eventually, his major work, Conjectures Concerning Dark Stars, was published in 1783. It is hard to imagine a more dramatic title for such measured mathematics. The book did not instantly overturn the world. Contrary to popular myth, people did not wake the next morning gasping into the streets because light had been trapped overnight. Intellectual change is slower than sunrise. Many readers treated the dark star system as a useful calculating device rather than a literal truth. Others resisted it. Some admired the mathematics while doubting the physics. After all, if light is trapped, why do we see stars? Why do objects dropped from towers fall straight down? Why do stars show no obvious shifts in position? These were fair questions. Modern hindsight can make old objections seem silly, but they were often grounded in serious reasoning. The evidence available then was incomplete. Telescopes had not yet transformed observation. Inertia was not yet properly understood. Stellar distances were vastly underestimated. If stars were relatively near, Earth's yearly motion should visibly shift them against the background. Since no such parallax was seen with naked eye instruments, many concluded Earth must not move. The real answer was that stars are unimaginably far away, but without that knowledge, skepticism was reasonable. This is worth remembering whenever history is told too neatly. Science advances through evidence and argument, not heroes effortlessly defeating fools. Still, Michel had changed something fundamental. He moved light from the exempt. That sentence is simple. Its psychological impact is not. For countless generations, humans had occupied the apparent middle of the cosmos. Our world felt like the still platform around which lights revolved. To become one planet, among others, was more than an astronomical adjustment. It was a shift in self-standing. We were no longer seated on the cosmic throne. Now the phrase cosmic throne deserves a little caution. As mentioned before, not every geocentric worldview treated Earth as glorious. Some regarded the heavens as purer realms and Earth as the heavy, imperfect center below. Yet centrality still implied structural importance. Losing that centrality mattered. And this pattern would repeat later. The sun would lose special status as one ordinary star. Our galaxy would lose special status as one among billions. Even our visible universe would become one region of a larger cosmic story. Science has repeatedly relocated us from imagined centers without diminishing the wonder of being here. Michel began one of the earliest great relocations. There is another subtle beauty in his model. It restored coherence among the planets. Mercury and Venus, which never stray far from the sun in our sky, naturally do so because their orbits lie inside Earth's orbit. Mars, Jupiter, and Saturn wander more widely because they lie beyond Earth. What looked like arbitrary behavior from an Earth-centered view becomes orderly from a Sun-centered one. When patterns simplify under a new perspective, scientists pay attention. Of course, Michel did not get everything right. He still favored circular orbits, which meant his system retained some apocycles. Perfect circles had deep philosophical appeal, and nature had not yet confessed its preference for ellipses. That confession would come later through Johannes Kepler, so heliocentrism began not as a finished truth but as a better scaffold. That too is common in science. First models that move in the right direction are often imperfect. They matter because they reframe the problem. Think of trying to solve a puzzle while holding the box upside down. The first great improvement may simply be turning it around. Michel also reminds us that intellectual courage is often quiet. He did not storm institutions with theatrical speeches. He reasoned carefully, wrote meticulously, and trusted mathematics enough to let it challenge intuition. That can be harder than drama. Intuition says the sun moves. Mathematics says perhaps Earth does. Intuition says stillness feels real. Reason says sensation can mislead. Intuition says we are central. Evidence says maybe not. These tensions are timeless. Even now, many truths feel wrong before they feel clear. Why did heliocentrism eventually win? Not because it was emotionally satisfying to be displaced. Quite the opposite. It won because later evidence strengthened it. Galileo's telescope would reveal moons orbiting Jupiter, proving not everything circles Earth. Phases of Venus would support heliocentric geometry. Kepler would refine planetary paths into ellipses. Newton would later explain orbital motion through gravity. Michel planted a seed others would grow into a forest, yet planting matters. Without the initial willingness to question the central Earth, later discoveries might have taken longer to interpret. Evidence often requires a conceptual home before it can fully speak. This has echoes far beyond astronomy. Many personal misunderstandings persist because the wrong assumption sits silently at the center. Change the assumption, and tangled experiences reorganize into clarity. Perhaps a friendship was strained not by malice, but by fear. Perhaps a failure was not proof of inability, but evidence of poor timing. Perhaps a recurring problem survives because the frame is wrong. The universe and the human mind both reward reframing. It is also fitting that Michel came from a world already changing. The Renaissance was stirring renewed interest in mathematics, classical texts, navigation, art, and inquiry. Printing spread ideas more widely. Exploration expanded maps. Confidence in inherited certainties was becoming negotiable. Cosmic change often accompanies cultural change. When people redraw oceans, they eventually redraw heavens. And yet, none of this made daily life feel different immediately. Bread still needed baking. Winters still arrived. Markets still opened. Families still argued over ordinary matters. The stars overhead looked much the same. Scientific revolutions frequently alter meaning before appearance. The Earth moved long before it felt moved. That remains true today. We live in a relativistic universe, a quantum universe, an expanding universe. Yet sidewalks remain perfectly walkable, and tea still cools in ordinary ways. Deep truth and everyday life coexist peacefully. Michel's legacy, therefore, is not just a new planetary diagram. It is a lesson in humility and method. Humility because our preferred position may be mistaken. Method because careful reasoning can reveal realities hidden from direct sense. He also teaches patience. Some truths require generations to mature. A bold idea may need better instruments, sharper mathematics, and later minds to complete what it begins. As you listen now, perhaps in darkness, perhaps with rain outside or city light beyond curtains, it is easy to forget how strange it once was to imagine Earth in motion. Today, children learn it early. Up once it asked people to overturn the testimony of their own senses. That is no small request. and still greater requests were coming. If Earth circles the sun, then perhaps the stars are far beyond imagination. If our world is a planet, then perhaps the heavens are not made of separate perfect substance. If our place is movable, then maybe many things once fixed are open to revision. By the time John Michell had suggested that light might be trapped, the old cosmic arrangement had been disturbed but not yet defeated. A new idea existed. That is not the same as a new consensus. Many scholars still preferred the older Earth-centered model. Others found heliocentrism mathematically elegant, but physically doubtful. After all, if Earth truly moved, where was the evidence one could see with ordinary eyes? The sky still appeared to circle overhead each night. The ground still felt steady beneath one's shoes, sandals, boots, or scholarly slippers. What Michell had offered was a rearrangement of logic. What was still needed was a rearrangement of sight. Then came a device so modest in size and so enormous in consequence that it changed humanity's relationship with the sky forever. The telescope. Now the telescope. Now the telescope. Now the telescope was not originally invented by Galileo. Versions of it appeared first in the Netherlands in the early 17th century. Built as optical instruments that could make distant objects appear closer, they were useful, intriguing, and probably inspired at least one person to stare suspiciously at neighbors from a slightly unethical distance. Galileo heard of the device in 1609. Rather than simply admire the concept, he built improved versions himself, grinding lenses and refining magnification. Then he did something that seems obvious only because history has already happened. He pointed it upward. This is one of those steps that sounds simple and changes everything. Sometimes the greatest breakthroughs come not from inventing a tool, but from asking a new question with it. When Galileo turned the telescope toward the moon, he did not see a perfect, smooth heavenly sphere, as many traditions had imagined. He saw mountains, valleys, shadows, rough surfaces, and irregular terrain. The moon looked less like a divine lamp and more like a place. This mattered deeply. For centuries, many thinkers had divided reality into two zones: the imperfect earth below, where things changed, decayed, broke, and behaved inconveniently, and the perfect heavens above, where celestial bodies moved in flawless harmony. But the moon had craters. That may not sound revolutionary now, but philosophically it was a hammer blow. If the moon had rugged landscapes, then the heavens were not made of an entirely separate perfection. The sky and earth might belong to the same physical universe after all. One wall had cracked. Then Galileo looked at Jupiter. There, beside the giant planet, he observed tiny points of light that changed position night after night. At first glance, they looked like stars, but they moved with Jupiter, sometimes on one side, sometimes the other. These were moons. Today, we know them as Io, Europa, Ganymede, and Callisto, 4 of Jupiter's largest satellites. But to Galileo and his world, they carried a larger message. Not everything orbits Earth. That single fact weakened geocentrism dramatically. If little worlds circle Jupiter, then Earth is not the mandatory center of all motion. The heavens can host multiple centers of orbit. Nature had just demonstrated flexibility where doctrine preferred singularity. Imagine insisting that every road in the nation must lead to one city only to discover entire functioning towns connected to each other elsewhere. The old claim becomes harder to maintain. Galileo next observed Venus, and here the evidence became even more striking. Venus shows phases much like the moon, sometimes crescent, sometimes gibbous, changing over time. In the old Ptolemaic Earth-centered system, Venus could not naturally display the full set of phases observed, but in a sun-centered arrangement, where Venus orbits the sun inside Earth's orbit, the changing geometry makes perfect sense. Venus was quietly siding with Copernicus. The sky itself had begun testifying. Galileo also saw that the Milky Way, long perceived as a pale, cloudy band across the night, was composed of countless faint stars when viewed through magnification. What had looked like mist became multitude. That discovery carried emotional force as well as scientific meaning. The universe was larger than it appeared. This pattern repeats often in astronomy. Improve the instrument. Enlarge the world. Naked eye reveals stars. Telescope reveals far more stars. Better telescopes reveal galaxies. Later instruments reveal clusters, filaments, background radiation, exoplanets, black holes, and phenomena so strange they sound like drafts from speculative fiction. Each time, the boundary of known reality moves outward. Galileo stood near the beginning of that long expansion. Now it is tempting to tell this story as a neat conflict between science and ignorance, but history is rarely so tidy. Many scholars engaged seriously with new evidence. Some religious thinkers supported astronomy. Some scientists disagreed among themselves for technical reasons. Institutions reacted in mixed ways. Still, Galileo became a central figure in controversy because he argued forcefully, publicly, and sometimes with a level of sharpness that did not always improve diplomatic outcomes. He was brilliant, witty, and not especially committed to making enemies slowly. This combination can accelerate both progress and trouble. Galileo defended heliocentrism with confidence, sometimes mocking opponents in print. That gained attention but also resistance. Eventually, his conflict with church authorities led to trial, condemnation, and house arrest. The details are complex, involving politics, personalities, interpretation of scripture, scientific standards of proof, and institutional power. But one broad truth remains. Evidence challenging established worldviews often meets friction. People do not surrender familiar realities lightly. And why would they? World views are not just diagrams. They are homes for meaning. When someone says the Earth moves, they may sound to modern ears like they are making a technical claim. In another age, they could also seem to threaten philosophy, theology, hierarchy, and common sense all at once. This still happens today in new forms. Facts that appear narrow can carry emotional consequences far beyond their data. Yet despite resistance, telescopic evidence could not be unseen. Once mountains were seen on the moon, perfection was complicated. Once moons were seen around Jupiter, exclusivity was broken. Once phases of Venus were observed, heliocentric geometry gained strength. Once the Milky Way dissolved into stars, scale expanded. The telescope did not merely add facts, it altered the kind of universe people inhabited. That distinction matters. Before the telescope, the heavens were largely a visual dome. After the telescope, the heavens became a landscape layered in depth, texture, and multiplicity. A flat ceiling became an ocean. There is something deeply human in how we extend our senses. Glasses sharpen sight, ships extend travel, writing extends memory. Microscopes reveal hidden smallness. Telescopes reveal hidden largeness. Every tool changes not only what we can do, but what we can imagine. Without telescopes, moons around other planets would have seemed speculative curiosities. With telescopes, they became nightly observable realities. Entire arguments shifted because invisible things became visible. This is a useful reminder. Whenever certainty depends too heavily on unaided perception, the world contains more than the senses first report. Galileo also contributed something beyond observations, a style of inquiry grounded in measurement, repeatability, and mathematized nature. He championed the idea that the book of nature is written in mathematical language, whether or not one likes the metaphor. The practical result was powerful. Motion, trajectories, falling bodies, celestial behavior, all became candidates for quantitative treatment rather than purely philosophical speculation. The sky was no longer only interpreted, it was measured. That shift helped unite heaven and earth under common laws, a process later completed magnificently by Isaac Newton. The same gravity that drops an apple also guides the moon. The same mathematics that describes a cannonball can describe a planet. Once again, boundaries dissolved. It is worth pausing to appreciate how emotionally strange this must have felt. Imagine living in a world where stars seem decorative and heavens seem symbolic, then learning that planets are worlds. Moons orbit elsewhere. The moon has mountains. and the Milky Way contains immense crowds of stars. It would be like discovering the wallpaper in your hallway is actually a doorway to a city. Reality suddenly gains depth. That is what telescopes do best. They create depth where eyes once saw surface, and the consequences of this expanding view continue. When later astronomers built larger telescopes, they found nebulae, then realized some were entire galaxies beyond our own. Still later came radio telescopes, space telescopes, infrared observatories, X-ray telescopes, and instruments sensitive to wavelengths human eyes never evolved to detect. Galileo's small tube of lenses began a family line of cosmic translators. Even now, when a new observatory opens, humanity often experiences the same old pattern: surprise, enlargement, humility. We keep learning that the universe is not only bigger than we thought, but bigger than our habits of thought. There's also a gentle philosophical lesson here. Galileo did not move mountains physically, but by seeing mountains on the moon, he helped move minds on Earth. Sometimes perspective changes through literal perspective. Stand on a hill and a town reorganizes itself below you. Use a microscope and a drop of water becomes crowded. Use a telescope and certainty becomes negotiable tonight. Perhaps you are listening from a bed, a sofa, a chair near a lamp, or beneath a blanket while the room grows quieter. Around you, familiar objects hold their shapes. The walls seem still. Daily life feels local and manageable. Yet beyond that roof lies a sky once transformed by a tube of glass. Jupiter still carries its moons. Venus still cycles through phases. The moon still bears shadows and craters. The Milky Way still spills its innumerable stars across dark places. And each of those sights whispers the same message. Things are rarely centered where we first assume, and edges are rarely where we first assume, and edges are rarely where we first draw them. Galileo did not finish the cosmic relocation that Copernicus began, but he made it visible. He gave people reasons to trust that Earth could be one moving world among others. He widened the stage and reduced our claim to the middle. Once Earth had been moved from the middle of the cosmos, one might imagine humanity would become permanently cautious about declaring new centers or new edges. History suggests otherwise. When one throne is removed, the mind often starts polishing another. After Copernicus and Galileo, the sun took on a new dignity. No longer merely a bright lamp circling Earth, it became the anchor of the solar system. Planets, including our own, traveled around it. Seasons, daylight, warmth, and orbital order all tied themselves to this glowing star. It was natural to wonder whether the sun might now occupy a larger cosmic importance. Perhaps we had not lost the center after all. Perhaps we'd simply mistaken which object sat. This is a very human move. When certainty shifts, we often relocate confidence rather than surrender it. Yet, as astronomy advanced, even the sun's promotion would prove limited. Beyond the solar system stretched the stars, and among them ran one of the oldest visible mysteries in the night sky. A pale, misty band crossing darkness from horizon to horizon. On clear nights, far from city lights, it appears as a luminous river, softly textured, brighter in some regions, thinner in others. Ancient cultures interpreted it in many ways. Some saw spilled milk, giving us the name Milky Way. Others imagined roads of souls, celestial rivers, smoke from cosmic fires, pathways of birds, traces of gods, or bridges between worlds. Such interpretations were poetic, practical, sacred, and deeply human. But what was it physically? That question lingered for centuries. To the naked eye, the Milky Way looks cloud-like. It resembles faint mist more than individual stars. Galileo's telescope changed that perception by revealing that the band was made of enormous numbers of unresolved stars packed so densely that human vision blended them into glow. The cloudy stripe became a crowd. This was a remarkable step. The sky was not sparsely decorated with lights on a dome. It contained staggering populations of suns. Still, one question remained stubborn. How were those stars arranged? Were they scattered evenly in all directions? Were they embedded in a shell around us? Did they form a great disk, a cluster, or something stranger? And most importantly for tonight's theme, where were we within it? In the 18th century, astronomers began trying to answer this with increasing seriousness. Among them was William Herschel, a musician turned astronomer whose work dramatically expanded knowledge of the heavens. Herschel built powerful telescopes, discovered the planet Uranus, catalogued nebulae, and attempted something bold. He tried to map the Milky Way. His method, called star gauging, was ingenious for its time. He counted stars in many directions of the sky. If more stars appeared in one direction, he reasoned that the stellar system extended farther that way. Fewer stars might indicate a nearer edge. Using this approach, Herschel concluded that the Milky Way was a flattened system, somewhat like a grindstone or lens with the sun located near the center. There it was again, another center, another comfortable middle, another place for us. Now Herschel was not being vain or mystical. He was reasoning from available evidence. His assumptions seemed sensible, that stars were spread roughly uniformly and that his telescope could see to the boundaries of the system. Both assumptions would later prove incomplete. But his effort was scientifically admirable. He was transforming the Milky Way from mythic glow into measurable structure. Even mistaken maps can be noble if they move understanding forward, and Herschel's map did something psychologically powerful. It gave humanity a new home concept. We no longer lived at the center of the universe, perhaps, but maybe we lived near the center of the star system that mattered most. A downgrade, certainly, but still respectable. It is almost charming how often we negotiate with humility. If not cosmic royalty, perhaps regional management. The trouble was dust, interstellar dust to be precise. The Milky Way contains vast clouds of gas and dust that block visible light, especially along the dense plane of the galaxy. Herschel's telescopes, impressive though they were, could not see through these obscuring regions. In many directions, he was not measuring the edge of the galaxy at all. He was measuring how far sight could travel before darkness intervened. This is a profound lesson in science and in life. Sometimes what looks like a boundary is only a veil. Because the dust limited vision, the sun seemed centrally placed. We could see roughly similar distances in many directions, before light faded or was blocked. It was a false symmetry produced by incomplete access. The mind is vulnerable to this kind of error. Stand in fog, and the world may appear equally bounded around you. That does not mean you stand at the center of the landscape. It means visibility has limits. For decades, and in some ways longer, humanity lived inside a fog of stars and dust while imagining itself centrally located. Meanwhile, the Milky Way itself became more richly understood. Telescopes revealed star clusters, variable stars, nebulae, and structures hinting that the galaxy was not a tidy uniform disk. Yet certainty about our position remained unsettled. This often happens during scientific transitions. The old picture weakens before the new one stabilizes. During the 19th century, photography entered astronomy, allowing long exposures that captured faint